Welcome everybody, you're watching Mr. Fugu Data Science. Thank you to my recent viewers and subscribers, I greatly appreciate it. Remember to turn on that notification bell. Don't forget to hit me up on Instagram and Twitter, and if you can, please help support this channel. I'm on Buy Me a Coffee. Here's my username. We got a lot going on with lasso and ridge regression today, which I will explain, but first we need to talk about linear regression. If you're familiar with those concepts, please skip forward. I'll provide a timestamp so you can get directly into ridge and lasso. Here we go. Linear regression has a few problems. For instance, predictions for linear regression will have low bias and high variance. This will contribute, later we'll see, to overfitting. When you're trying to improve your predicted accuracy, consider changing the bias, which will in turn lower your variance. When you're trying to interpret linear regression, we need to understand that you're assigning a coefficient for each predictor. But what do we do when we have large numbers of variables outweighing our actual number of observations? This is problematic. For instance, if you had a lot of columns but very few rows, you would need to get rid of some of your variables in order to simplify for interpretation, because your model would be too complex. We could think of linear regression like this. We have some predictors which are x1 to xn or x minus n, and the response variable which is our y. We have our true model here with y equals our intercept and whatever terms that we have with our weights. Now this right here is our error term. This is going to be interesting. We'll notice this a little bit later on. There's a distinction that we need to notice, which is our estimated model, where you have this hat notation above everything. We are trying to find our parameters beta and our intercept of beta naught. And we want to find the best value of our beta, which is going to minimize our sum of squares error. Since this is linear regression, we will be able to say that our error equals this right here. You need to consider that your errors are going to be added together so we can achieve our residual sum of squares. And therefore, you need to realize this is what's going on. The simplified version is this, of course, where we're summing everything together. The sum of the true y and the predicted values. Now, let's look at something. We're trying to basically acquire the best fit line for our given data. So we're trying to basically move this line around to minimize the error that we have, which would be the distance between this line and this point. Now the next thing I want to show you is I ran a linear model with those made up data I had before, which you'll notice right here. If you want to pause the video and see how I set that up, feel free to do it. But just notice something. I set this line, I showed the error lines for this, and this is approximately the best line for the given data that we have. And if you see this red dot, this dot is one of our outliers. With linear regression, this is kind of a problem and it will shift your line. So you have to be aware of that. Also, I want you to notice something here. Look at where this line is. It's not at the origin anymore. It's shifted up. So you've had some scaling or standardizing and centering of your data. That's something you should always look into and consider. For instance, if your data are on varying scales, be aware of that and always keep that in the back of your mind. Now this plot that we have right here is our linear model. I'm going to explain what's going on here. Zoom out just a little bit for us so we can see what's going on. Assume that this red line is our best fit line, and this red dot right here is our actual point. And the distance from this point to this line is our error. And we're saying that our estimated value, which should have lied on this line, should have been 85.1, whereas the observed value that we have is 87.2, okay? And you'll see that this right here, our expected value should have been the mean, which would have been the peak of this right here. That's just what's going on. And here's our line equation. This is telling us that these were the specific parameters that best fit our line with this intercept. That's all that's going on with this, to give you an idea. There's 4 basic assumptions for linear regression that you need to be aware of if you're not familiar. A linear relationship, so you're checking that the independent and the dependent variables have a linear relationship. You could check this out by examining a scatter plot of x and y. You need to also look for independence, okay? You need to check that there's not correlation or some form of relationship between the residuals and the variable y. You may want y to be independent, okay? Use a scatter plot of the residuals versus your fits to establish this. The next thing that you need to look for is constant variance. This in practice can be an issue or unrealistic, but consider that the variance of the residuals should return return the same value for all values of x. To plot this and check what's going on, use a scatter plot of the residuals versus the fit and look to see if there seems to be a relationship or a pattern. Then you need to establish an assumption of normality. Your distribution should be approximately normal. Take the residuals and plot with a histogram and see if it looks like a somewhat normal distribution. Let's first get into overfitting, since that's what's going on with linear regression, and this get a handle of what this really is doing. And overfitting is a problem. It doesn't generalize your model. It's only giving you something that may be conducive for your training data. Your model is going to fail for new observations that are used for prediction. So let's look into this. High bias causes underfitting, which will mean you have low variance, and you're clearly missing your relationships within your data, which means that your model is too simplified. Now, you may get consistent results, but you're inaccurate for training on average. Whereas if you have a high variance, you may be overfitting and you're accounting for actual noise, which is irrelevant. But in turn, you get an accurate model on average, but it's just inconsistent. So the variance and bias depicted here, we would say that this is a good fit because we have low bias and low variance, and your points are basically centered here. Overfitting will have a situation like this where they're kind of scattered and you're having a high variance. And then you have the other situation where it's an underfit, where you have low variance, but you have a high bias. And you'll say to yourself, well, do I always want to get rid of the variance? Well, we'll get into that. For instance, when we're underfitting, if we just had this straight line like it was linear regression, but obviously our data look like we got this hump going on, right? So obviously it's some kind of polynomial, but we didn't figure that out. So we underfit the data and now we have some high bias. Now the low bias and low variance situation is just right. And that means that we're pretty much fitting our data here and we have some outliers. And when we overfit and have that high variance, we're basically going about and finding every single contour of our line, approximating it to our data, and we don't show any deviation with it. And that's problematic. And that's something you could consider of what's going on with linear regression. A side note, understand that OLS, ordinary least squares, doesn't care which independent variables are important. You're only finding the unbiased coefficients. This should bring us to a question. Does the model with lowest residual sum of squares provide best results? The short answer, nope, because you're overfitting. Now the bias variance trade-off is important because the bias is a measure of how far an estimate is from the true value. And you noticed above, when we're underfitting, our line had more error because the distance of the points were further away from the line, but it was best fit for test data. The variance, think of this as two things. One, it's the reciprocal of the precision. Also, it's the spread of your data, essentially the variability for some prediction of our data point of interest. Let's look at a couple things with low variance and low bias algorithms. For instance, low variance, we're going to have less complex and more rigid structure of an algorithm, such as regression, naive Bayes, parametric algorithms. Whereas if we had something that's low bias, it's more complex, but it's flexible. Such as decision trees, nearest neighbor, nonlinear, non-parametric algorithms. Please pay attention to this. We're interested in total error. Well, the total error is our bias squared plus the variance plus some irreducible error that we can't control. And I need to highlight this. Don't fall into the trap of thinking that we need to reduce or minimize bias at the expense of variance. I need to say this again. Don't fall into the trap of thinking that we need to reduce or minimize bias at the expense of variance at all cost. This is problematic and not good thinking, okay? Understand that I'm saying, well, something is wrong with my model since I have high bias. Fundamentally, I think that I need to fix my model. And yes, increasing the variance will give us a more complex model and on average a better prediction. But this is only part of the story. This is due to the fact that you are trying to model your data and not a hypothetical situation with a long-term averaging effect. Hence, I'm trying to model my test data. I'm not trying to get a really good model for my training data, which doesn't work on my test data. Let's look at this bias variance trade-off. Here's our total error in the black line, the variance in the teal blue color, and the bias in the red. And this line coming down is basically in the middle. It's a little off, but that's your sweet spot that you're looking for your model complexity, okay? We have on the y-axis your error, which is increasing, and on the x, the model complexity. And when you run to the right over here, when you overfit, think of that as your OLS for your linear regression stuff. And going left, you're underfitting, which is what we're trying to kind of do. We're trying to get that happy medium, okay? Let's look at something that we need to consider, which is stepping into multiple dimensions, because this is where linear regression can give you some of the problems. So here's some of the shortcomings with it. Let me highlight this for you. For example, when you have a large amount of predictors, think your columns, versus your observations, which are your rows, you're going to have some difficulty of establishing that your columns are actually independent. If we're setting this up in our vectors, you're going to have your y, which is a n vector. You're going to have a matrix of a n by k for your x, k for your betas, and an n for your errors. And if we expand our errors here, you're going to notice something. We want to minimize the amount of error, right? So let's expand this, set the derivative, and rearrange. And here's what our estimated beta will look like. And there's something you need to understand. When you're using your matrix or your vector notation, this only works if the inverse exists. So beta works when the columns are independent, all right? But when you're dealing with large numbers of features for your columns or low observations such as your rows, then you end up having x, which is invertible. So this occurs because the x transpose x won't be linearly independent. We can fix this by adding a term, our diagonals, which is lambda, which will help us. And that's what brings in lasso and ridge. Remember, ridge is your L2 norm or error that you'll see. It's just a squared penalty term. It's used for shrinking. We're trying to minimize the coefficients for our standard error. We take the same thing we had above, which is in turn our residual sum of squares, and we add that term on. Don't worry, I got you covered if you want your vector stuff, but just look at this. We now added our shrinkage term to the tuning parameter, okay, which is used for our regression coefficients. When lambda is large, the coefficients of beta approach 0. This will in turn create bias. So now you're increasing your bias. When you increase your lambda, the coefficients of beta will approach 0. They do not become exactly 0 with ridge. Remember that. Now, on the flip side, when lambda becomes quite small, you approach the least squares. And in this case, you're increasing the variance again and reducing your bias. Here's our ridge regression. Here's our linear regression. At this point, when your lambda, let's scroll up, when your lambda is approaching infinity, you're going to have your underfitting, overfitting here, right here, where we're at 0. And we notice that linear regression has about, for this particular example, a predicted of 1.8 for our error. Whereas we have down here about a 1.2 for the ridge regression. So it means that we're trying to reduce the amount of error that we have, and in doing so we have to use our penalty term and increase that value. So we're penalizing our coefficients in order to get this lower error prediction. Ridge reduces the complexity, not the features. Okay, you're not removing any features with ridge. Also, it's just shrinking their effects. And think of trying to find a new line that doesn't fit so great to your training data in order to create a better prediction overall. You may not have thought about this, but your degrees of freedom are effectively your shrinkage. It's kind of confusing, but this is our ridge versus our ordinary least squares. So here this dot right here, this ridge estimate, is what you're going to find. This ordinary least squares estimate here is our optimum spot. So basically, if you take this blue circle and increased it to that dot right here, would be the optimum position. But it causes problems because now you're effectively changing your betas here because you have beta 1 and beta 2. This ellipse contours are your residual sum of squares. The innermost one has the smallest residual sum of squares. We're trying to minimize the size of the ellipse and the circle at the same time with our constraint. If you increase the size of the circle, then it's going to approach towards our best value for our OLS. But in doing so, it's going to affect your betas, which are going to increase. And then now what you're doing is increasing your variance, but you're decreasing your error. And in this case, if we make more of these contour lines and keep coming out, you would have a shrinking of this sphere, which would mean you have more features going towards 0 and increasing the amount of error. And let's think about something. Let's scroll down. the circle and the ellipse are constrained. So since you're trying to make both of these, minimize both of these at the same time, you have to consider something. As you increase your lambda, your betas prefer to go towards 0. When your lambda goes to 0, you end up with your least squares, which means that this circle basically just shrunk into itself. As lambda approaches infinity, then your betas approach 0. And the ridge estimate is basically when they touch. The OLS point where it best fits the training data sets the lowest bias at the center here. Alright, let's clarify that figure above, which is kind of confusing. There's a trade-off between this penalty term and your residual sum of squares. A large beta may give you better residual sum of squares, so increasing the circle, but it's going to increase your penalty term as well in order to decrease that error. This means that you would have to try to have the circle reach the center of the ellipse to get a better residual sum of squares, but you're going to end up overfitting. For ridge, you're tuning the circle by either increasing or decreasing its size. The betas have an effect on your residual sum of squares. Let's think about something. If we are changing the size of the circle, for instance, we are decreasing the circle and increasing the size of the ellipse, then your beta 1 will approach 0. So how do we actually find the optimal lambda? Well, that's interesting because you consider cross-validation. In the case of RStudio, use glmnet for your library and then call the cross-validation function from there. Here's some considerations. I said this before and I'm saying it again. Consider scaling your features and centering so that your coefficients are not mistaken because of their sizes. You will only want to have them disregarded due to their importance, remember, not due to their magnitude. Interpretation of your coefficients. You're interested in predictions of your y. This is not an inference problem where you're looking to evaluate your beta hat. We need to think about the fact that the variables may be correlated. Another note, as the penalty for overall coefficients decreases, the individual coefficients may increase. Again, overall coefficients may decrease, but the individual coefficients may increase. But what is going on with that? You're squaring your terms, remember? And you're adding them together. If we had two coefficients that were not penalized from the original least squares, say we had one that was 7 and one that was 1, and we use our lambda from ridge regression, let's say we're decreasing by 2. We end up with 24 here, and the other one, we'd end up with 8. But what does that tell us? If the variables were correlated, you'd be able to penalize the smaller variable more to make up for the larger one. This cannot be done with lasso on the other hand because you do not have squared terms. Lasso on the other hand is going to be your L1 norm or error. It's just the absolute value of it right here. And this causes the coefficients to exactly shrink to 0. As you increase lambda, more coefficients will go towards 0 and less predictors are selected. The downside of this is not strictly convex. And what does that even mean? If you had two features which were identical, then you wouldn't be able to distinguish them to do a minimizing. And in that instance, you would need to use elastic net, which would give you a unique solution in that circumstance. So let's look at OLS versus our lasso, and you notice it's not a circle, it's a diamond shape now. There's a slight difference with this diamond shape, okay, since we're doing feature selection. The tip of the diamond, when it reaches that ellipse, that's the coefficient corresponding to the axis that will be shrunk to 0. Notice this is a 2D situation. If we had this increasing in dimensions, you would have more of these diamonds protruding outwards in different dimensions, which would give us the ability for the corners to approximately touch more often to that ellipse, which would potentially shrink more coefficients to 0. If we created more of these rings, made this diamond smaller, we would lower our betas and have more error. So let's look at this a little bit more. Here's a difference. Ridge, the penalty term will never make your coefficients exactly 0, and you're always going to retain all of your features, even though you may have just noise. This dotted line, horizontal, is our linear regression. The purple one is our lasso, and the bluish purple one, blue one, is your ridge. Here's the takeaway from this. We're using our DFs on our x-axis and our expected error. Think of your DF as your shrinkage parameters, and on average, you have around 24 features selected using lasso, whereas ridge, you have all of the features at all times used. That's something to take note of. Here is an example using ridge where we have your mean squared error versus your lambdas. And there's a few things that you need to notice with this. The first thing, here's our test data. This little hump right here where it's convex, this is our optimum point that we want. We're going to notice that this training data starts at the bottom here, which is really low error. We have a higher error here at the start for test data, suggesting that we have overfitting. At this point right here, this suggests where we have the best variance and bias trade-off, our low variance, low bias. After this point, we start to have issues with underfitment. So that's the takeaway. This recap, when you have a really small value for lambda, essentially you're going towards the linear regression. Let's look at the comparison of ridge and lasso plotted in respect to the coefficients versus the lambdas. On the right side, this is your lasso. On the left side, this is your ridge. Ridge will approach 0, never set your features to 0. You noticed here that these three right here, these three, LCP, age, and glycine, are set to 0 immediately. So if you start at 0, and you'll see that they're basically useless features. That's one of the takeaways from this. Also, if you wanted to say which of these features are important, remember, cross-validation would be the use case of that. But as always, I'd like to say please like, share, and subscribe. And if you subscribe, turn on that notification bell. If you thought this is useful and would like to support the channel, go to Buy Me a Coffee and look for my handle. But as always, like, share, and subscribe. And if you subscribe, turn on that notification bell. See you in the next video. Bye.